You are live.
We are live, so we will wait a couple of seconds. Maybe some participants still want to join us. Okay, so I think the Swiss company, we should be precisely on time. It's 9:30 now. Hello, everybody, and welcome to our webinar on PAROX, or Paramagnetic Oxygen Measurement. My name is Volker Rüsekopf, and I'm working as Key Account Manager with Angst+Pfister Sensors and Power. In this role, I support our customers in the field of gas detection, and oxygen is one of the big topics therein. Together with me is Jacques Faber, the mastermind of the PAROX technology. And in the next 30 minutes, we will give you an insight in PAROX, in the working principle, in applications, but also, of course, in the technological benefits. You will have a chance to ask questions after our presentation. We have a Q&A session at the end of the webinar. Certainly, these 30 minutes will not be enough to address all topics. So please do not hesitate to contact us after the webinar. Our contact details will be shown at the end of the webinar, or you simply contact us through our website, sensorsandpower, one word, .angst-pfister.com. During the webinar, we will do some polls where we ask you for participation. The result of these polls will only be for us, and we will certainly not share any of your personal details. But for now, I better stop and lead over to Jacques. Jacques, stage is yours. Please go ahead.
Welcome all participants to this webinar on PAROX, our solution for paramagnetic oxygen measuring. My name is Jacques Faber. I'm the head of development gas sensors within Angst+Pfister Sensors and Power. And I'm the former owner of the brand of PAROX, which has been acquired by Angst+Pfister beginning of this year. I'm now working for more than 12 years in the business of paramagnetic oxygen measuring, and I'm more than proud and happy to give you some introduction over this measuring principle. First, let us have a look on the agenda. Who are we? I just want to give a brief introduction about who is Angst+Pfister Sensor and Power. I would like to spend some time on the measuring requirements, on the typical applications, and mainly on the measuring principle. Then after this, we're quickly gonna talk about the influences and mainly about the countermeasures, and of course the outstanding advantages of the paramagnetic measuring system, and to give you some product overview of what can we offer. Who is Angst+Pfister Sensors and Power? To give you just a short overview of who we are and what we are especially good at, let me quickly introduce Angst+Pfister Sensors and Power. We are an independent daughter company of the Angst+Pfister Group with more than 1,000 employees worldwide and a customer base of about 60,000 satisfied customers. We are a leading supplier of sensors for gas, pressure, temperature, geometry, but also power supply solutions are in our product portfolio and many more. Last but not least, I would like to mention that Angst+Pfister Sensors and Power also provide engineering services in regard to developing solutions according to your special measuring task. If we dive into the gas sensors, you will see the broad know-how that we have, and you will see it also on our webpage under SP www.angst-pfister.com. SP stands for Sensors and Power. You see the whole range of products that we provide, but today we are going to focus on these gas sensors. If you dive into these gas sensors, you will see the broad know-how and product portfolio, and you will notice that mainly on the oxygen measurement, we have a very broad range of products. This portfolio has been completed this year by integrating the PAROX business into our organization. PAROX is an internationally, since more than 30 years, well-established business with a broad customer and application base. And the aim is very clear. It's the integration of PAROX is meant for offer to our customer the full range of oxygen sensors for all kind of applications. But now we are going to focus on the PAROX itself. So coming to the requirements, depending on the application, the requirements for the measuring of oxygens might be more or less demanding. Most mentioned requirements are definitely the accuracy. Of course, for high demanding and precise measurement, for process controlling, for example, this is a very important requirement. But second requirement we often face is also the gas mixture, because of possible cross sensitivities due to the presence of multiple gases. Then what is the specific application and the operational condition? Where do you measure? Do you measure in the desert, on the mountain, in a submarine? This all needs to be clearly defined in advance. The sensitivity is an important issue. Are you measuring high percentage volume of oxygen, or are you measuring in the ppm range? Then last but not least, the response time, where, for example, the measuring result is required for a quick reaction, for safety relevance, for example. So these are all requirements which need to be addressed before it comes to a selection of the right measuring.
So now it's time for our first poll. Please tell us your technical requirements. Submit your answers before we continue. We'll give you a couple of seconds time for this, and then we move on. Okay. So should have been enough time. We can move on with our presentation.
Principle. As we just were talking about the different requirements, so depending on the requirements, there are different measuring principles which can be used for measuring oxygen. So just to give you an overview over the most common oxygen measuring principles, these are definitely what we are talking now, the paramagnetic principle, but also electrochemical cells might be a solution. Zirconia cells is also tunable diode laser absorption spectroscopy, so-called TDLAS, and the fluorescence quenching, and ultrasonic oxygen sensors. So you see there are many principles which can be used for measuring oxygen, but it's definitely depending on the requirements. Today we are going really to focus on the paramagnetic principle and mainly on the PAROX. What are typical applications for the PAROX? So one application is definitely the biogas monitoring, as O2 is a reference gas for fermentation process within the gas vessels. This is a very often found application. Another one is the SEMS, so the continuous emissioning monitoring system for the process analysis. We have a lot of application with the air separation units to measure the degree of purity of the oxygen. And especially now during COVID, a lot of producers of oxygen were in need of paramagnetic measuring systems. But also excess oxygen analysis, for example, in the food industry or for sealing, where you don't want to have any excess oxygen to avoid any oxidation process to come up. And there are many, many more applications for the PAROX. This is actually just to name the most important.
So now this is the point where we have our second poll. Please vote, so we move on afterwards. Okay, see the results coming in. We go ahead.
So to better understand the capabilities, but also the limits of the paramagnetic oxygen measuring, it helps really to understand the working principle. You see here the mechanical structure of the principle as well as the relevant components. The principle of the paramagnetic measuring is based on the physical property of O2, that it is paramagnetic. This means that oxygen molecules are attracted by a very strong magnetic field. And this is exactly what we do. We create a very strong magnetic field. In between this magnetic field, where we want the oxygen to be concentrated, we place two glass spheres filled with nitrogens, the so-called dumbbells. They are suspended with a very thin wire, and there is a small mirror attached on this dumbbell. And as soon as you have a concentration of oxygen here, it comes to a deflection of this dumbbell, which also comes to a deflection of this mirror. So with a light source projected on a small mirror, which is over here, this is the light source, and then rejected to positioning photodiode, the deflection can be measured. Now, depending on the measured deflection, an electronic board will generate a light current, and this current is applied to a very small wire, which you see over here and over here. The current through this wire placed within the existing magnetic field, which we have here, creates a counterforce back to the initial position. So you get actually an equilibrium between O2 forces and the pushing back of this wire. So at the end, the light comes back to this middle position, and this current is directly proportional to the O2 concentration. And just to give you an idea how this looks like in real, you have here these dumbbells. You have here the south pole shoe, the north pole shoe, you don't see it here. You have the mirror. Just to give you an idea about what size we are talking, these are 2 millimeters. So this is a very thin, very small item. And here you see this wire loop around the dumbbell to create the counterforce. By understanding now a little bit better the principle of the paramagnetic oxygen sensors, and also looking at the size of this sensor and looking of this mechanical deflection, you can easily understand that there are some influences which are physically defined, but there are also countermeasures. And I would like to come to the influences that we have on this measurement system and possible countermeasures. First of all, we have definitely the temperature. Our sensor is temperatured on 55 degrees. So this is actually to make sure that the temperature influences from outside is minimized. Why is the temperature has the temperature an influence? It is very simple. This is a physical phenomenon. If you have the oxygen sensors, the oxygen molecules, excuse me, in between those pole shoes, and if you have a higher temperature, you will have those molecules which will be spread all over the measuring cell. And therefore, the measurement system itself has less oxygen in between this area where it is relevant. So in that area where you have the dumbbell. The consequence is that the electronics thinks there is less oxygen, so therefore the signal is lower, and therefore I give less current, meaning by that the output of the oxygen sensor is less. Even that you have exactly the same amount of oxygen within the measuring cell. So what you have is actually, if you have a rising temperature, you will have a lowering in the oxygen output. This can be, as a countermeasure, can be solved insofar that you have a heated measuring unit. That's what I said previously, that our oxygen sensor is temperatured on 55 degrees. Another very important influence is the pressure. Here it's exactly the different way around to the temperature, because here, if you have a higher pressure within your gas path, you will have the oxygen molecules which will be compressed, and therefore you will have more oxygen molecules between those pole shoes. The sensor itself measures more oxygen, even that within the whole gas you have the same amount of oxygen. So therefore, you will have the situation that if the pressure rises, the signal of oxygen measured will rise too. It goes so far that, for example, a 10 millibar change of atmospheric or barometric pressure change will cause, when you measure 100% oxygen, will cause 1% change in reading. Just to give you an idea. This can be compensated by a so-called back pressure regulator, where you regulate the pressure above the atmospheric pressure. Then the next one is the flow. Here again, you have seen the structure of the paramagnetic oxygen sensor. And if you have a higher flow, you will have turbulences within the measuring cell. So therefore, you will have an unsteady reading. And therefore, we suggest to use a static internal bypass, which is increasing the flow when you increase the flow from outside, but in a way that you still have a very moderate flow through the measuring cell, or you go on a dynamic external flow regulator, which is a small device where the flow can be regulated, and there you can have from 20 to 90 liter per hour you can apply to the sensors, and it will be assured that the flow through the measuring cell will be adequate to 100 milliliter per minute. which is 6 liters per hour. Another issue is the humidity. Humidity can change the readings, and therefore we suggest to use dry gas or use a gas cooler in the gas conditioning system. So here again, you might have some changes in the reading. And last but not least, of course, if you have dust or dirt within your gas, or this might obstruct some gas path or the light way, and this may also change your readings. So after talking about all these influences, we really also need to address the outstanding advantages of PAROX, because if you do the right countermeasures for those influences, you might have really outstanding advantages. So first of all, the principle is fully linear. This means you need only a zero and a span calibration to calibrate the sensor. Then you have a very low cross sensitivity with other gases. You have no maintenance, as there are no wearing parts. Of course, you need calibration from time to time, but this is very much depending on your application. You have a very long lifetime. So when a sensor is running in steady conditions and with well-filtered air, it runs for years and even tenths of years. You have a precise measuring in the volume percent range. So if you are looking for a really ppm application, then as you can see, this is not the right instrument to use. But for a volume percentage range, it is really a good solution. And last but not least, it's definitely a continuous measuring system. It is meant for put in and let it run. You can let it run for years and years. So this is really a 24/7 application. So before coming to the end, and after having discussed a little bit the principle and the influences and the countermeasures, I would quickly draw your attention on our product portfolio. First of all, we have the transducer, which is the PAROX 1200, which you can have in different specification depending on your requirements. So measuring range 0 to 25, 0 to 100%, or output of 0 to 1 volt, 0 to 4 volt, 4 to 20 milliampere. So there are different specifications which you need to confirm us before using the sensor. Then the next one is our analyzers with the built-in PAROX 1200. The analyzers which all begin with this 2. So meaning by that you have here this 2. So this is the 2000, the 2100, 2200, and actually these are only in difference. It's only the cabinet. So here you have a 19-inch rack, you have a transportable, and you have a wall-mounted analyzer, which displays you the oxygen value and which you can have with different options. Last but not least, I would like to show the accessories. So the options you can have, mainly you have here back pressure regulator, filter, flow regulator, and flow display. So there are several accessories which you can get in order to minimize the influences that you have on the measuring. So this was a brief introduction in this large field of paramagnetic oxygen sensors, and I'm more than happy to answer your questions with my colleague Volker.
So we're almost done with our webinar and the presentation, and this now is the last poll before we move over to the Q&A session. So last time, please share your answers with us. Okay. Good. So
thank you very much for your kind attention, and we are looking forward to your question and to your measuring requests to support you. Thank you.
So, thank you, Jacques, once again. We now hear a lot about PAROX, and before we switch over to the Q&A session, I'd like to introduce the third participant here. Besides Jacques and me, our product manager, Dr. Naumann bin Tanwir. He will also be available now in the next 5 to 10 minutes for our Q&A session. If you want to submit a question, please use the questions function that you find at the bottom right of your screen, of your Livestorm screen. Some questions are already there, so we'll start with those, and I will leave it to Jacques and Naumann to answer these questions. So the first question I see here is, what about the influence of the measuring gas temperature?
The influence of the measuring gas temperature.
Yes.
What is the influence? I unfortunately do not really understand the question.
I think the question is, how much does the temperature of the measuring gas affect the precision of reading?
Okay, I got it. Sorry. So you have two things. The one thing is definitely the outside temperature that you have where you put your oxygen sensor. But I think here it's more the question of the gas itself. So you must think about the gas. It goes through the measuring cell. The measuring cell is heated up to 55 degrees. So of course the gas which comes out afterwards after the sensor will be higher. It will be heated a little bit up, but it's still in a very normal range. So what we also can supply is to have some so-called gas heater. That means that the gas, first of all, does a path for a longer path through the heated measuring cell, and by that it can be ensured that the gas through the measuring cell has a constant temperature already before entering.
Okay, thank you, Jacques. So next question, here is one very practical. What is the typical power supply needed?
The power supply is 24 volts. So, and that's the volt, and due to the fact that it's heated, it takes about more or less between 12 and 15 watt.
Okay, thanks. And how often do we recommend a 0-point calibration?
That's what I said or tried to say in the presentation. It very, very much depends on the application that you have. If you have a very precise application, it definitely makes sense before you start measuring to do a quick calibration. This is a thing, it lasts for 1-2 minutes, or it takes 2-3 minutes. If you have a constant going application, there it makes sense to have maybe every week or every month, but to make the calibration every week or every month. But actually it's really depending on very much on the application that you have. So there is no one answer to this question.
Okay, but basically if we leave any answer open, we cannot answer all the questions here. You can of course contact us afterwards. We will show our contact details again, and we can get into a deeper discussion with all of you.
And we will, and the question will still remain, so we can answer you afterwards.
Yes.
To make sure that they are not lost.
Yes. So there's one question that we received from several participants, and it refers to the cross influences. So are there any cross influences with other gases?
Of course, this is,
For example, with
with.
You just lost Volker. I believe he's referring to hydrogen sulfide.
So something happened with my connection.
Yes.
Can you hear me and see me
Yes,
again?
Yes.
we can hear you. Actually, the hydrogen, just for cross sensitivities, it's in so far the paramagnetic system is very, very good in regard to cross sensitivities. There is a table which is available in the manual where you see all the different gases, and if you have some gases where you know that the amount of cross sensitivity gas is quite high, you can do with some calculation, you just can delete actually the influence. But this parameter for calculating is normally with all gases very slow. There's actually just one which is quite high, that's the nitrogen dioxide. But others are quite low, and if you know that you have the clearly defined gas, you can calculate so to eliminate this effect on a calculatoric way.
Mm-hmm. Maybe I add something here. We have also a lot of other technologies in our portfolio, and what Jacques is referring to being very low, it's extremely low in comparison to other technologies that we have overall available for oxygen sensing. So that means that indeed there are some gases which have an influence, but in comparison to other technologies, the influence is extremely low. So we can really quite clearly say in this case that the paramagnetic oxygen sensing is very selective to oxygen.
Mm-hmm. Okay. So here's one question about certification. Is there any product like from the PAROX series which can be used in the ATEX or explosion areas?
No. No, not yet. This is definitely an area where we are not in. Till now, it's not really planned, because you need to know that the certification process is a very, very high demanding, and till now we are not in this area. No.
Mm-hmm. Okay. So if someone wants to have a fast measurement, there is a question here. What is a typical T90 rise time for paramagnetic sensors?
This also cannot be answered just with one figure, but if you have just a sensor itself, you have a pathway which is quite small, then you will get a reasonable result within 3 minutes. If you have a sensor which is built in...
Sorry to cut you. 3 minutes, you said?
3 seconds, sorry.
Okay, that's very important.
Sorry, 3 seconds. And if you have, of course, the sensor which is built into an analyzer with a quite long pathway with a filter and whatsoever, then it might take up to 10 seconds. Mm-hmm. It somehow depends.
Mm-hmm.
Mm-hmm.
We have a lot of real practical questions here, like this one. What are typical gas flow rates?
The gas flow rate is, if you just use an oxygen sensor without any bypass, then you should go to this 100 milliliter per minute, which corresponds to 6 liters per hour. But in order to make sure that you don't destroy anything, it would really be useful to use a bypass or a so-called flow regulator. The flow regulator actually is a mechanical part, so there is no electronic required. And the flow regulator is always built in within our analyzers. And with the flow regulator, you can apply from, let's say, 20 to 90 liters per hour, and it makes sure that the flow through the measuring cell is always at this 6 liters per hour.
Okay.
I
running-
see one question that I really would like to quickly answer, because this is a very often a question. Do you need a 2-point calibration or only 1 point? That's a very important one. At the beginning, you need a 2-point calibration, but afterwards, if you have a stable condition, then it's also possible to do only 1 point. So meaning by that, just a 0 point, because the inclination, it gives you 2 point, 1 point, 2 point. And afterwards, if the inclination is right and you are in a steady environment, you cannot just do the 0 and you will have the good results. But sometimes it makes sense to make the 2-point calibration.
Mm-hmm. Okay. So I would say there's one last question. Again, please contact us or let us know how we can help you after the webinar. But this last question is one which is probably interesting to some of us. It's simply, can we get a copy of the slideshow? So I think, yes, we can provide a copy. If we can provide it as download, or if we can do it in face-to-face contact or direct contact, is something what we will check. But basically, we are happy. If you're interested, we will be very happy to share it. Okay, so it's 10:06, and we are coming to the end of our webinar. We hope that you got a good insight into the PAROX technology. As said, it can never cover all of the aspects, all of the topics, but it was hopefully good enough to give you some taste about what we can do. If you think that you have an application for us, or if you think it's basically a good solution, but you need some other features, please speak with us. We can do modification on our product. We are flexible, and we are always willing to work as closely as possible with you. If you like what we're doing, please let us know, drop us an email or see our website. Otherwise, we will continue with a series of webinars in the future, even for other technologies. Please follow us on LinkedIn, Facebook, or Twitter, and you will always be updated. Thanks to Naumann and Jacques for the participation, for the work done, and I wish all of you a nice day, a nice Thursday, and see you next time. Thank you.
Thank you very much.
Thank you.
Bye-bye.
Thank you. Have a nice day. Thank you. Bye.